All right. Well, thanks very much to the organizers and all of the staff at the Fields Institute for really going above and beyond to make this event happen online. So, as was said, I want to talk about some joint work with Rolando de Santiago, Ben Hayes, and Daniel Hoff. So this is about maximal rigid subalgebras of deformations. So there's a bit to unpack here in terms of well, what is a maximal rigid subalgebra and what's a deformation? And I'll get to that. But I think at the beginning, I should just kind of tell sort of the story of how this fits in to the program for classifying 2-1 factors, and give some context for our results. So I think, this has been discussed at least a few times so far in the conference, but yeah, here's how the story starts. So these capital Greek letters are going to usually denote countable discrete groups. And from any countable discrete group, one can, well, we want some sort of conjugacy class condition. So I'll usually assume ICC, so all of the conjugacy classes. But one, the identity, are infinite. Okay. And yeah, for one of these groups, you can get a unitary representation on little L2 just by left shift of the natural basis by the group. So that's the left regular representation. And you can take those unitaries and close them up in the weak topology, or take the double commutant. I guess if I want to close in the weak topology, I should take the span. And that defines the group von Neumann algebra, and that's a 2-1 factor. All right. So the big question in classification. Oh, well, maybe other than, these things are very important examples of 2-1 factors. I should say really that the main, or one of the main reasons they're interesting is that the projections that are sitting in here, those are corresponding to invariant subspaces. So if you're interested in the representation theory of a countable discrete group, this is always a canonical representation, and this von Neumann algebra really tells you how this decomposes. So kind of the big overarching thing is to try to classify these things. So what properties of the group can be used to distinguish the group von Neumann algebra? And of course, there are several properties, and some of them have been discussed already. So amenability, has strong structural consequences by the work of Kahn. There's property T, there's property gamma of Murray and von Neumann. So those are just kind of on-off things. You either have them or you don't. You kind of want invariants that take sort of broad numerical ranges. And so there are a couple of these sort of related invariants that exist for groups and dynamical systems associated to a group and even to unfactors. So there's this L2 Betti number, and I really want to focus in on this in a second, so I'll tell you what that is if you don't know. And of course, that a lot of people were in there in the inception of L2 Betti numbers for groups, but that comes from work of people like Atiyah and Giger and Gromov, etc. There's a notion of cost for dynamical actions of groups. That's Gaborio and Levitt. And then there's Voiculescu's microstates free entropy dimension. And I guess we've seen a little bit about microstates from talks on Kahn embedding. But these are all sort of numerical invariants. They attach numbers, and those numbers can take a continuum number of values. And so the question is, do any of these things have are any of these things von Neumann algebra invariants? So those are very big open questions. In particular, if the L2 Betti number is a von Neumann invariant, that would imply the free group factor problem. I should just write that out. So the free group on M generators being isomorphic to the factor of the free group on N generators, does that imply? The ranks are the same. Well, M equals N, really. Of course, free groups are not isomorphic because their abelianizations have different rank, but of course that has no purchase in von Neumann algebra theory because abelian rank is not defined. Anyway. Okay, so that's kind of the big picture. So the work that we were interested in was specifically about some consequences of things for Betti number 0. So let me just talk a little bit about homology and Betti numbers for a sec, just to define what they are, and that's kind of important for the context of why we were interested in the results that we got, and how our results kind of make sense of some of these techniques in group cohomology at the von Neumann algebra level. So so let's talk a little bit about this. So what is what's going on here? So we start with a unitary representation of a group. And so what's the one cohomology? So a cocycle is a map, one cocycle. Is a map from the group into the Hilbert space that has this Leibniz identity. So these are, if you like, and so these are affine. These correspond to affine actions on the Hilbert space, whose linear part is the representation. You can think about them as kind of it's a discrete group, so this doesn't quite make sense, but kind of tangent vectors at the origin for this action. That makes sense if it's like a Lie group or something like this. So you can look at the space of all the cocycles. Now there are kind of boring ones among these, and these are the inner one cocycles, and those are simply where you just have implemented by taking this kind of differential against a fixed vector. And then you have something that's slightly more general than this. So you have almost or approximately inner. And that's to say it's locally approximated by so one thing I'll point out is there's a theorem of Guichardet, and this is sort of one thing as a consequence of our techniques that we can kind of grapple with at the von Neumann level now. So I'll just put it here. But this is a very useful and remarkable fact, is that so these approximate inner cocycles are the correct closure, or the closure in the correct topology for the inner ones. And so if this representation has spectral gap, for what I'm saying, that's going to be for the left regular. That's just going to be where gamma is not amenable.
I'm sorry, Thomas. There's a question from Ilya Farah. He's asking, how is this representation pi sub g of z a unitary?
That's not a unitary. That's just a vector.
So but you wrote that pi maps gamma into u of HP. Oh, sorry, C. Sorry, ignore me. No, sorry.
Yeah, it's just yeah, it's a cocycle, so it's going into the Hilbert space, not the unitaries. So if you have spectral gap, and for the left regular, again, that's you can just gloss that as being non-amenable, then approximately inner implies inner. So the inner things are already closed, and so you can think about this space of all cocycles, and let's just do it for the left regular. Modulo the inner ones, I'll just write that as B1 by common convention. Oh, let me just write this as L2 of gamma to be clear. And so this turns out to be a right L gamma module. So if you just multiply the vectors on the right instead of the left, all of the algebraic identities are preserved, and inner things go to inner things. And so this has a dimension, and so the first delta Betti number of the group is the dimension of this thing. Okay, great. And so in particular, if you're non-amenable, then the Betti number being 0 is the same as saying, well, there's no interesting cohomology. Okay. And so kind of a sub-question to the big question, which is still itself a big question, if that makes sense, is just having 0 L2 Betti number von Neumann algebra invariant. And Jesse has a theory of L2 rigidity, which is, you know, a von Neumann algebraic property, so it is an invariant, which is the, you know, it is a natural and the correct analog of vanishing of Betti number for a von Neumann algebra, but it's not. So every group von Neumann algebra that's L2 rigid has vanishing Betti number, but the other direction is difficult. Still pretty wide open. But okay, so well, that's you know, a hard question, but you can kind of you know, find another sub-question to your question that maybe is tractable and still interesting. And so what are some consequences, or what are some things that have 0 L2 Betti number? So let's write down an example of something with 0 L2 Betti number, or a general type of example. So if we start with H1 and H2 being property T groups, well, let's look at a group gamma, and let's have 2 property T subgroups. And let's assume that their intersection is infinite. So if you have this setup, and let's just assume also, well, yeah, and let's assume that they generate gamma. Okay, so if we have 2 generating subgroups with property T and infinite intersection, then you have vanishing L2 Betti number. Okay, so I may you know, time permitting, try to sketch this, because it's germane to the results that I'll discuss in the von Neumann algebra setting. Hopefully I have a little bit of time to indicate how that works. But okay, so here's the sub question. So if you have a group gamma with positive L2 Betti number, is L gamma isomorphic to any L lambda, where lambda decomposes as above? So this was this question was posed by Jesse. at an AIM workshop. And so, well, okay. We were extremely ambitious, and then still extremely ambitious in our question, but slightly less ambitious. Well, now I don't know what level of ambition this one is at. It's kind of not for me to judge because we solved it. So the answer is no. This cannot happen. Okay, so this is some at least and property T here is not super essential. You can just have you can just replace that with each of the Betti numbers. Vanishing. I just wanted to write the question as Jesse posed it. So that gives you some indication that, well, okay, maybe these Betti number questions may not be totally hopeless or out of range of techniques. So we have so I want to talk about the ideas here that that helped us resolve this question. But before I do that, are there any questions over this background? I'll just kind of pause here for a few seconds. Okay, so there's a couple of questions here on the chat. So the first question, one question is what is meant by a von Neumann algebra invariant? And that is, so I'll just give the concrete. I'll answer the question concretely for L2 Betti number. So so if I have two group von Neumann algebras that are isomorphic, okay, and so plenty of these things can be isomorphic without the groups being isomorphic. Does that imply that, well, the groups may not be isomorphic, but maybe there's still some information about the groups that survives? And so if the Betti numbers survive, then that would be the L2 Betti number being a von Neumann algebra invariant. And if isomorphism of the group factors tells you that both Betti numbers are 0, if one or the other is 0, then you could say that the Betti number 0 is a von Neumann algebra invariant, and you can play the game for any of the other things that I talked about. So does that clarify that? Okay, great. Okay, so then the other question that popped up is what is the significance of the sub question? So of course the question of whether the thing that I wrote here, whether Betti numbers, all of them are regardless of whether it's 0 or not, is a von Neumann algebra invariant. I pointed out that implies the free group factor isomorphism problem. The sub question of whether Betti number 0 is a von Neumann algebra invariant, that is kind of less of a kind of a it's not connected to such a kind of a long-standing open problem. But the significance, I guess, is that the technical difficulties you seem to have to overcome are related with continuity of if you have two different generating sets, is there some sort of way to kind of transfer the cohomological properties from one to the other? And this is related to continuity of the microstate's free entropy dimension. So there's kind of a lot of related conjectures here, or there's a lot of these related invariants that I was talking about, microstate's free entropy dimension, fixed cost for a group or cost of an action, and the L2 Betti number. They're all kind of very similar, and there's lots of estimates that go between them, but there's not kind of really sharp things that say they're kind of all the same. And if they were all the same, that certainly allows you to, for instance, if you have positive Betti number, having good microstates models. So I think Vaughn gave a talk about cusp forms and the group von Neumann algebras for PSL2Z, and having microstates approximations for cusp forms, for instance, would be something that number theorists would be interested in. So it's a little bit kind of harder to address the significance of that in the sense that it's just related to a lot of very technical internal open problems in the field, with possible applications in other directions. So I hate to be a little bit wishy-washy on that, but it is important, and I hope that at least justifies it a little bit more. Okay, great. So let's then kind of talk about the von Neumann algebras. Our results are not about cohomology. They're about the von Neumann algebra version of cohomology, or at least the von Neumann algebra version of a one cocycle. We can kind of talk about von Neumann algebraic versions of one cocycles individually without having a coherent cohomology theory. Again, it's one of these difficult problems that seems to elude us having an interesting cohomology theory. But these are the analogs of one cocycles. And these are extremely important because of Popa's deformation rigidity. It's right there in the label. Theory. So this has, this is, something that's developed over the last 15 to 20 years. Starting with some fantastic work of Serene Popa, who really, brought this whole, concept or strategy to, in one kind of big chunk, right into existence. So the deformation rigidity has really revolutionized classification. It's really so far the only tractable method for classifying large families of factors. I should say probably non-gamma ones, to be honest about that. But yeah, it's really kind of the way that we understand the classification of factors. So what is a deformation? we have M is a 2-1 factor, just in general. And there's a bit of data that's going into this definition. So a deformation of M is well, okay, I'm going to put more stringent conditions on it than just a general deformation. So this is what Popa calls an s-malleable deformation. But I'll just say deformation just for shorthand, and I always mean this. So it's a collection of objects. So one, you need an over 2-1 factor. So this thing M is now kind of swimming around in this bigger 2-1 factor M tilde. Again, this, you want a unital inclusion. And then you have a 1-parameter family. Alpha of T of automorphisms of the over factor M tilde. So it is a 1-parameter group in the sense that the additive identity holds. And then kind of the last piece that you want is you want an involution of the over factor. Oh, and this is, of course, it's you really want to strongly continuous, right? So you have this involution that fixes the subfactor M, and so that it reverses the direction of the flow. And I can't really, explain there's not one particular reason, why the existence of this thing is necessary, but it comes in so many sort of important ways in the theory. It's kind of hard to quantify. So this is really kind of the extra special, non-obvious thing that you need to make this definition kind of sing. And again, this was all discovered by Popa beginning in his early works on the subject. So the importance of the beta and just deformations in general. Okay. So that's what a deformation is. And so it turns out, and I can't really get into the construction here in too much detail or any detail at all, but this is a generalization of a 1 cocycle. So if you have a 1 cocycle C, and it doesn't really matter into what any representation. The representation is kind of irrelevant here. You can use that to construct a deformation of L. An s-malleable deformation. So in this way, you can import cohomology theory into deformation rigidity, and this is a major source of a way of kind of getting some structural properties of the group on Neumann algebra. So you can, and of course, if you look at the differential, this thing will exist on a dense subalgebra. Again, I can't really get into the fine points of this. If you look at this differential of a deformation, this gives you a derivation of the algebra into some bimodule. And of course, derivations of algebras are well understood to be the analog of homology for but there are plenty of deformations that don't come from one cohomology in any way, shape, or form. All right. So the second part of deformation rigidity is the rigidity. So that's equally important. And so what does it mean that something is rigid? So, well, let's set it up. I'm going to have M, and then I'm going to have this s-malleable deformation of M. And so we'll say that a subalgebra is rigid if alpha t converges uniformly to the identity on the unit ball of Q. So converging, so yeah. On unit ball in the 2 norm. Okay. All right, so example, so if Q has property T, so there's a generalization of property T from groups to von Neumann algebras due to Kahn and Jones, then Q is always rigid. Or any embedding and any deformation. Okay. In fact, you can take that as a definition of property T for a von Neumann algebra. Okay. So there's a couple of sort of questions here that we're kind of open and that we were able to address to get the result that I told you before of this kind of non-isomorphism for these kind of amalgamated property T things with things with positive Betti number. So, well, okay, let me just make another definition. Well, yeah, so, okay, I'll say it this way. So I'll say that, okay. So if we have Q inside of M, and I have some intermediate algebra here, P. And again, I'm fixing some deformation. So we'll say that P is a rigid envelope. Or Q, if it is a unique maximal rigid subalgebra containing Q, or the deformation alpha. So unique and maximal are important here. Okay. So in cohomology theory, it often is interesting to take a subgroup that has vanishing Betti number, so a subgroup with property T or something like this, and then try to find try to establish that there's sort of a unique largest subgroup that contains it, which has vanishing Betti number. So that's kind of an important linchpin for these kind of homology vanishing results that I talked about. And so this question of whether you could do the same thing for a deformation in a von Neumann algebra to kind of recover some of these cohomology techniques is exactly what we were able to establish. So here's the theorem. So if we have a 2-1 factor M, we have some s-malleable deformation of it. We have a subalgebra Q and M, which is rigid. And so that the commutant in the bigger thing is contained back inside of M. So I can't really say this is crucial, but this is replacing some sort of mixingness in the homology theory. If you know what that means. If you don't worry too much about it. When you have a rigid thing, then there is a rigid envelope. And moreover, if you have, oh, maybe this is part 1, 2. If you have Q1, Q2 in M rigid, and their intersection, when you commute it with, when you look at the relative commutant of the intersection of in M tilde, that's sitting inside of M, then Q1 and Q2 have the same rigid envelope. In particular, the algebra that they generate has to be rigid. Okay. So that's the main theorem that we established. And so really the key innovation here was kind of finding really the correct analogs for homology vanishing techniques. I think I'm running sort of short on time, so I can't. I think well, I can't really quite get into it explaining exactly how that goes. But I guess here is kind of a quick corollary. Is that result above? So I have gamma with positive L2 Betti number. Then gamma is not isomorphic to L lambda, where lambda is generated by two subalgebras with property T, whose intersection is infinite. So why is that? So here's the argument. So L of H1 and L of H2 inside of L of lambda are rigid for any deformation. That was property T. So by property. Okay. Great. Well, then, as I said, well, okay. So now you take the non-trivial one cocycle. So pick a non-trivial one cocycle here. For gamma, you can do that because the Betti number doesn't is non-zero. And construct a deformation. Now, this is working for the left regular representation of gamma. So this has the right mixingness for every infinite. Or for every diffuse subalgebra. So that's good, in particular for the intersection. And so this mixingness assumption, so I should whatever, I'm not going to talk about what that bimodule is, but that thing is sitting back inside of L lambda / L gamma. You're assuming they're isomorphic. And so by our main result, we have that this deformation that you get from C converges uniformly on the unit ball of gamma, but this is a contradiction. It's a contradiction because you can check that if you have a non-trivial one co-cycle, it has to be unbounded. And just by the literal description of what this deformation does, you can check that the unboundedness implies that it can't converge uniformly. And so that does it. Okay, so my time is basically up. So that's the strategy. And I said before, as I said before, you know, this gives you know, some hope here that, you know, we may kind of have a foothold into maybe beginning to start addressing this question of whether vanishing Betti number is a von Neumann algebra invariant. That being said, you know, here's the next logical question to check. If H1 is amenable, this also has vanishing L2 Betti number, and H2 still has property T. With all the assumptions, the intersection is infinite, they generate the group. Is that going to be isomorphic to a group von Neumann algebra with positive Betti number? You know, so far we have some kind of stab at addressing this, but so far the techniques that we've written down have to, you know, there's still a non-trivial amount of work to do to kind of push it to this case. But I'll just leave it there, and thank you for your attention.